Okay, so this next section is about measuring concentrations of compounds in solution. This is going to be split up into two lectures also, a part one and a part two. We want to be able to calculate the concentration of a solute in a solution in units of moles per liter, which is molarity, and we use solution concentrations and calculations. Describe how to prepare a solution of given concentration from the solute and solvent, or by dilution of a more concentrated solution. So again, this will be broken up into two sections where we talk about concepts and do some problems, and then another section or another part where we do a lot more of the problem solving. Okay, so let's go ahead and get started. So measuring concentrations of compounds in solution. The concentration unit we're going to use is called molarity, and it's the number of moles of solute per exactly 1 liter of solution. Okay, and just a reminder, you've learned this before in your previous chemistry class, that when you have a solution, it's homogeneous. The solute is the dissolved substance. The solvent is what does the dissolving, and together they make the solution. So this molarity unit is written a number of different ways. So, for example, if you write 0.512 m NaOH, this is an uppercase M, you would say this as 0.512 molar NaOH. And molar is short for 0.512 molarity NaOH. Now, when you write the NaOH there, that is the solute. So this means 0.512 moles of sodium hydroxide in 1 liter of solution. So these all mean the same thing, and you need to understand that because sometimes you say it one way, sometimes you say it another. In calculations, you're going to use this, but when you write it out, you're going to use this up above because it's a lot more brief and concise. So it is common also to determine concentration of ions in solution. We'll find that later on in the book also. So you must remember that the formula of compounds are ratios of ions and atoms. So in this case, when we have CO2, we're talking about 1 carbon to 2 oxygens, or we could say you have 1 mole of carbon to 2 mole of oxygen to 1 mole of CO2. It's just a formula. This is an ionic compound. We could look at the atoms or the ions. If we look at the atoms, for 1 mole of K2CO3, you've got 2 mole of potassium, 1 mole of carbon, and 3 mole of oxygen. If you look at the ions, however, for 1 mole of potassium carbonate, you've got 2 mole of potassium, and you've got 1 mole of carbonate. So, how do you prepare a solution of known concentration? Well, this is how you do it. You weigh the solute. This is a volumetric flask, and a volumetric flask has 1 marking on it, and it's at the top, and you fill it to that mark, and that's the volume. So you have volumetric flasks that have 50 milliliters, 25 milliliters, 100 milliliters, 250 milliliters, and so forth and so on. So after you weigh the solute and you put it in here, you add the H2O and mix, and then you top it off to the final line. Okay, so you want to mix it, make sure it's completely mixed, and then top it off. And here you have a volume where you can calculate the solution. So if you have the mass of solute, you can turn that into moles of solute using the molar mass of the solute. And here, whatever this volume is, oftentimes it's milliliters, you turn it into liters. And then you take this, divide it by this, and you have the molarity. So let's take a look at this in practice. If 25.3 grams of sodium carbonate is dissolved in enough water to make 250 milliliters of solution, what is the concentration of sodium carbonate? I'm going to put a little dot here so that we know that that has 3 significant figures. What are the concentrations of the sodium and carbonate ions? So we want to calculate the molarity. In this particular book, they're not really making a distinguishing between different types of concentrations. We're going with molarity. So to calculate the molarity, we need the moles of solute divided by the liters of solution. So we're going to go ahead and divide this into a couple of little side problems and then put it all together. So how do we get the moles of solute? We're going to take our 25.3 grams of sodium carbonate and multiply by its molar mass, where you have 1 mole of sodium carbonate. And let's see, where's my calculator? Sodium is 22.99. A carbon is 12.01. And an oxygen is 16. With 3 of them, that's 48. So this is 105.99 grams. Okay. And I'm going to do something real quick here. I'm going to do the rest of the work on another sheet of paper. So far, we have 25.3 grams of sodium carbonate times 1 mole of sodium carbonate per 105.99 grams of sodium carbonate. And that means we have 25 over 125 is about 1/4, right? So 0.25-ish, maybe a little less, 25.3 divided by 105.99. And we get 0.2387 mole of sodium carbonate in our solution. Now, for the volume, we have 250 milliliters of solution. So we're going to multiply by 1 liter of solution per 1,000 milliliters of solution. And you get 0.250 liters of solution. We want to keep that 0 here because it is significant because of this decimal. Okay? So we put it all together and we get the concentration is 0.2387 moles of sodium carbonate per 0.250 liters of solution. And you never leave this as a ratio like this. You divide this number into that so that you get basically a number over 1. So divide this by 2.250, and we should get a number that's pretty close to 1, but a little less. And so we get 0.955 moles of sodium carbonate per 1 liter of solution. Now, what's another way to write it? You write it this way, 0.955 molar sodium carbonate. And that's the kind of answer I would expect to see on the exam. And this is the kind of work I would expect to see on your exam. Okay, so that's the molarity of the sodium carbonate. Now, what are the concentrations of the ions? Well, we're going to use this here as the jumping off point. Plus, we're going to say that for every 1 mole of sodium carbonate, you have 2 mole of sodium ion because of this 2 here, and you have 1 mole of carbonate ion. So if we want to calculate the molarity of the sodium ion, we would take this 0.955 mole of sodium carbonate per 1 liter of solution, and you'd multiply by 1 mole of sodium carbonate, and I'm going to put that on the bottom so these cancel, times 2 mole of sodium ion. And what you would end up is getting moles per liter here, and then I'm going to multiply this by 2. And so you would get 1.91 molar sodium ion. Likewise, we would do the same thing. Actually, I'm going to do something different. I'm going to start with this. 1.91 moles of sodium per 1 liter of solution. and I'm going to multiply by 2 mole of sodium ion per 1 mole of carbonate. And we're going to end up getting 0.955 molar carbonate. And there you go. We've calculated the concentration of the sodium carbonate in solution, the concentration of the sodium ion in solution, and the concentration of the carbonate ion in solution. Okay, so there's that. Now, a really important concept in chemistry is this idea. The concentration of a solution times the volume of the solution gives you the amount of solute. So C times V equals amount. Now, when our concentration is molarity, this amount is going to be moles of solute. So for example, calculate the moles of sodium hydroxide in 250 milliliters of 0.512 molar NaOH. First, we need to convert the volume to liters, and then we need to recall that 0.512 molar NaOH means 0.512 moles of NaOH per 1 liter. So I kind of put it all together here, where I take the 250 milliliters of solution and convert it into liters by multiplying by 1 liter over 1,000 milliliters. And here, what that'll end up doing is giving us right here the volume in liters. So this is the volume part. And here's the concentration part. So when we multiply these together, we get 0.128 moles of sodium hydroxide. So this is volume times concentration gives you amount. Now, this is especially important for dilutions. Many times in science, what you'll do is you'll take a solution, it's too concentrated, so you dilute it, but you want to know the concentration of the newly diluted solution. So this would be the original solution, and here's the dilution. Since we're talking about aqueous solutions, we're talking about adding H2O. So what I tried to do here is draw some lines close together to make it look like it's a darker color, and here a lighter color because it's less concentrated. Now, I've drawn it another way below down here. And here we've got V1 and C1, but instead what I drew is I drew little dots for the solute particles. So when you add H2O, notice the 5 solute particles still remain as 5 solute particles, because when you add solvent, you're not adding any more solute. So remember, C times V equals amount, so we have C1, V1 equals 5 solute particles. And here we have C2 times V2 equals 5 solute particles. So therefore, C1 V1 equals C2 V2. This is your dilution formula that you want to remember. Usually, you're given C1 and V1, and you're given V2, or you're allowed to figure it out somehow, and you're calculating C2. So when you rearrange this, what does this become? It becomes C2 is equal to C1 V1 over V2. And these are the same formula, just written slightly differently. Okay, so that's your dilution formula. Let's take a look at this problem here. What is the concentration of iron 3 ions in solution prepared by diluting 1 milliliter of a 0.236 molar solution of iron 3 nitrate to a volume of 1,000 milliliters? So we're given that the concentration, the C1, is equal to 0.236 molar iron 3 nitrate. So here's the iron 3 nitrate formula. Now, that's C1 for iron 3 nitrate, but they want to know what is the concentration of iron 3 ions. So we need to turn that into a concentration of iron 3, not iron 3 nitrate. Now, from this formula, we know that 1 mole of iron 3 nitrate is equal to 1 mole of iron 3, and is also equal to 3 mole of nitrate. Now we don't need this 3 mole of nitrate part, but we do need this part right here. Now this concentration can also be written as 0.236 moles of iron 3 nitrate per 1 liter of solution. Now we know that there's 1 mole of iron 3 per 1 mole of iron 3 nitrate. So when we put this all together, these will cancel and we'll have moles of iron 3 per liter solution, and we can see that's going to be 0.236 molar iron 3. Now, I'm about to show you a really neat thing about these particular types of concentrations and dilution calculations. So I want you to recall that C1V1 is equal to C2V2. And if we look above and we want to make a list of all the things we have, so far we have C1 is 0.236 molar iron 3. V1 is the amount that we dilute. So we're diluting 1 milliliter of solution. V2 is the final volume, and it says to a volume of 100 milliliters, so that's our final volume. Okay, and C2 is what we want to calculate. What is the concentration? So here's the formula. Here's all the stuff we need to use in this formula. We're solving for C2. I find the best thing to do is to rearrange all these things so that you have what you want on one side and everything else on the other. So this is not an algebra review. I'm just going to show you the formula. How I get from here to here, you should be able to do like that. Okay, so now we've got these weird things. We've got this is moles per liter. Usually you're measuring things in liters, not milliliters. So this seems awkward. But I'm going to go ahead and just plug these in here and show you how neat this is. So C1 is 0.236 molar iron 3. V1 is 1.00 milliliters. And we can write solution here, just like we can do here. And we put this over 100.0 milliliters of solution. And look at what happens. The milliliters cancels with the milliliters. And what are we left with? We're left with molar iron 3. So what's really neat about these dilution calculations is that you probably don't have to change any of the volumes into liters. As long as they're both milliliters, things will cancel. Okay, so let's see what we get. We're going to get 0.00236. And it would be okay to write it as 2.36 times 10 to the minus 3 molar iron 3 plus. Okay, so that's the dilution concentration. All right, and we're going to do one more problem here and take a look at this idea here. It's called serial dilutions. So serial dilution is where you want to make a dilution more than once. So let's say that you have a solution that is so concentrated that even if you take one part of it, 1 out of 100 part of it and dilute it, that's still too concentrated. So what do? You dilute it again. So those are called serial dilutions. So let's take a look at this idea here with this serial dilution. Okay, so you have 250 milliliters of 0.136 molar hydrochloric acid. So we're going to go ahead and try and draw that. So 250 milliliters. So this is going to be my little 250 milliliter container. So this is 250 milliliters. And this is 0.136 molar HCl. Okay, using a volumetric pipette, so this is a pipette that measures things very, very well. We take 25 milliliters of that solution. So here's our volumetric pipette. And now we have 25.00 milliliters of 0.136 molar HCl. So we've taken that 250 and we've taken 1/10 of it. And we dilute that to 100 milliliters in a volumetric flask. So we're going to add H2O. And I've got to make a 100 milliliter container. So here's my 100 milliliter container. It's shorter than that one. And we have 100.00 milliliters. And we want to know, well, we don't want to know the concentration here, apparently. And then what you do is you take 10 mils of this solution, and here's where things get tricky. So now you probably want to start using some symbols here. Let's call this C1, C1 here, and we'll call this V1. So here's the volume we're diluting, and here's its concentration. We will call this V2, and we'll call this concentration C2, okay? And now what we're going to do is we're going to take 10 mils of this solution. So here's my volumetric pipette again. And since we're only taking 10 mils, it's going to be this, 10.00 milliliters. And this has the concentration of C2. We're going to add H2O. And we're going to make another 100 milliliters. And we'll call this C3. So we've got C1, where we have the original solution. We took a little bit of it, diluted it, and we got C2. We took a little bit of this solution because it's still too concentrated, diluted it, and made C3. What is the concentration of the hydrochloric acid in the final solution? So let me show you how you go about doing that. So you actually set up two problems. First, you would have C1 V1 is equal to C2 V2. And this is what we're focusing on right here. Because between here and here, the number of solute particles should be the same. So C2 is C1 V1 over V2, which is 0.136 molar HCl. V1 is the initial volume, 25 milliliters. V2 is the final volume, 100.0 milliliters. And when we do this work, we can see that this is going to be 1/4 of that number. So 0.0136 times, I put an extra 0 in, 0.136 times 25 divided by 100, and you get 0.034. Now my calculator doesn't have a 0 after the 4, but I need one because this should have 3 significant figures. 0 molar HCl. So that's C2. Okay. Now this is the second problem right here, where we're going to have C2 times, and here this is going to be my V2, and I'm going to put that in quotes because I have this as V2, but this is the V2 for the second problem. It's equal to C3V3. So C3 is going to be C2V2, and I'm going to put quotes around that, so we know it's a different V2 than this V2, over V3. Now, do you see how the drawing helps me to see that this V2 and this V2 are different, but these two concentrations are the same? All right. So when I plug in the numbers here, I get 0.0340 molar HCl. Volume 2 is 10.00 milliliters, and then 100 milliliters. So C3 is going to be this number basically divided by 10. And there is the final answer for what is the concentration of the final dilution, 0.00340 molar HCl. And that's it for this lecture. There'll be a part 2, and you should take a look at that next.